All right, my friends, welcome back. Hope all's well. This is our penultimate class. We're working on NMR spectroscopy. We'll finish that next time. We'll do a lot of practice, and then you'll be all set for the final, which I have written. So we last time talked about how to tell whether protons are the same or different. There's two different kinds of same, and there's two different kinds of different. The two different kinds of same are homotopic and enantiotopic. Homotopic protons are interchangeable by an axis of symmetry, and by that I mean some kind of rotation of the whole molecule that trades places of the two protons and leaves the rest of the molecule unchanged. Homotopic protons are always identical. Then we talked about enantiotopic protons. These are interchangeable by a mirror plane of symmetry. But again, that mirror plane of symmetry must interchange the protons and leave the molecule looking exactly the same. And enantiotopic protons are identical except in a chiral environment. What do I mean by that? Protons that are enantiotopic are different if they are bound to a chiral molecule. And the reason this matters to you is in biochemistry, you will see that a proton can selectively remove one of two enantiotopic protons. It can tell the difference between the two. I can demonstrate that with a model and pretending that my hand is the protein, and I can show that to you, but it would kind of be a waste of time to do that in class. But if you want to see that, you can come talk to me during office hours and I'll show you. So it will be important at some point in your future to know the difference between homotopic and enantiotopic. Then there are different kinds of protons. Backing up. For our purposes on an NMR spectrum, homotopic protons will show up as the same NMR signal. Enantiotopic protons will show up as the same NMR signal. Now, how about protons that are different? Two kinds of different. One is diastereotopic, and the other is just plain different. So what do we mean by just plain different? This is different, and it's obvious based on the environment of the molecule. For example, this CH2 group here is different from this methyl group there. That's just plain different. Diastereotopic protons are generally protons that are on the same carbon, but are not interchangeable by an axis of symmetry and are not interchangeable by a mirror plane. So they are diastereotopic, and I will illustrate that in a little bit. Just plain different protons and diastereotopic protons will show up with different chemical shifts, different NMR signals. So what we want to do is go through a few examples, identify how many kinds of protons there are, how many signals we should expect, and then what's the relationship between protons. So methyl protons, always homotopic because they're always interchangeable by rotation around a carbon-carbon bond. So those methyl groups are homotopic with each other. What would you say about protons E and F? Same or different, E and F? Same. Okay. Are they homotopic or enantiotopic? They are enantiotopic because they are interchangeable by a mirror plane of symmetry. The mirror is the plane of the page. Okay, what's in front is a reflection of what's in back. Same with C and D. C and D are enantiotopic, and A and B are enantiotopic. Okay, we expect 4 different signals, 4 different NMR signals in this molecule. So are CH2 groups always enantiotopic? No, it depends. For example, I showed you propane. These two, HA and HB, are homotopic because if we draw in purple an axis that goes through this central carbon and is in the plane of the page, we call it a C2 or 180-degree axis of symmetry, interchanges A and B but leaves the rest of the molecule unchanged because the methyl group on the left is identical to the methyl group on the right. HA and HB are homotopic. But notice that once you break that C2 axis of symmetry, once you put something on the left-hand side that's different from what's on the right-hand side, suddenly the C2 axis is no longer there, and these two are enantiotopic. The reason the C2 axis is no longer there is when you do the pancake flip, the C2 rotation, the 180-degree rotation, now chloro's on the left and it used to be on the right. And for it to be a true C2 axis of rotation, when you do it, the molecule has to look exactly the same afterwards. Yes?
So it's because of the things that are attached to that central carbon that changes whether it's homo or antio?
That's right. The things that are attached to that, well, really the symmetry of the molecule overall, but in this simple example, the things that are attached determine whether it's homotopic or enantiotopic. One quick, I wouldn't call it a hack because it's almost more complicated than what I've taught you, but it's a thought experiment you can do to check whether protons are enantiotopic or not. So your thought experiment is to replace one of the two protons on a CH2 group with something else. So let's say we replace HE with something else, and we'll call it Q because we have a question about what it is. Replace HE with that, now replace HF with that, and then you ask the question, what is the relationship between these two molecules? You would say that they are enantiomers of each other because they have opposite stereochemical configuration. Therefore, you conclude HE and HF are enantiotopic. Enantiomers here, enantiotopic there. That's the thought experiment you can do to check. Okay? Yes, question? Did I see a hand? Yeah.
What did you say the red ones were?
Homotopic. And the way you can actually test homotopic in the same way, replace one of these with Q and then the other and see if you've got the same thing. Okay, let's do this larger, example. The methyls, we conclude, are methyl protons are homotopic. But what about protons K, L, and M versus A, B, and C? What do you see there? What's the relationship between those two? They're the same. What kind of same? Homotopic or enantiotopic? Homotopic. Good. How do you see that? What's the axis of symmetry is? The purple one. Okay, fine. I already drew the purple one. It was hard to erase. C2 axis of symmetry, 180-degree rotation. Somebody asked last time, what about those double bonds in the benzene ring? Because when you flip it over, those double bonds have changed places. Why don't we care? Resonance means that you can draw another resonance structure where those oops, that's a too big eraser. Yikes. Where the double bonds are actually here. And in fact, it would probably be best to represent the structure of benzene in this context as having double bond character, partial double bond character between all of those bonds. So that resolves the symmetry issue about the benzene ring. So you would say that not only does H, K, L, and M equal each other, but also that the methyl group on the left and the methyl group on the right are also homotopic. So you'd say these three are homotopic with each other, and then that those two groups are homotopic. So we expect one signal for those 6 protons. How about H, J, and I versus E and D? Well, it depends on what you're talking about. So if I zoom in on J and I, what's the relationship between J and I? They are enantiotopic. They're interchangeable. Good, by a plane of symmetry. So within this group, those two are enantiotopic, but the two CH2 groups are homotopic because they're interchangeable by an axis of rotation. Okay? We could similarly say that these 3 protons on the methyl group are identical, that these 2 protons on the benzene ring are homotopic, and HP would just be its own thing because it's not identical to any other proton. So we'd say 1, 2, 3, 4, 5 different protons. 5 different kinds of protons, 5 different NMR signals for this molecule. Yes?
So just to clarify, when we're talking about like the relationship between all of these protons, what matters for the actual imaging is just whether they are some sort of same to each other.
That's right. For the NMR spectrum, what matters is, are they just some kind of same, either homotopic or enantiotopic.
The other stuff is useful for...
The other stuff is useful for biochemistry. So 2 protons that are enantiotopic, you could have an enzyme that would remove HI but not HJ. Yep. Okay. Let's talk diastereotopic now. Your text gives you some rules for identifying whether protons in alkenes and cycloalkanes are identical or not. You can follow those rules, and they're pretty self-evident, but you can also apply what I've taught you about homotopic and antiotopic and diastereotopic. So if we look at this molecule, this alkene, it's clear that the methyl protons are identical to each other. We would say that those are homotopic. But what about HD and HE? It's probably obvious to you that they are different because one of them is cis to the chloro and one of them is trans to the chloro. In order to be identical in an alkene, they would need to be cis and or trans to the same things. So it's clear that they're different, but what kind of different? There are 2 differents. One is diastereotopic and the other is just plain different. So to determine whether something's diastereotopic or not, it's usually that the 2 groups are attached to the same carbon, but then you look for an axis of symmetry that makes them interchangeable. And if you don't find that, you look for a mirror that makes them interchangeable. And if you don't find any of those, if both are no, then you conclude that the protons are diastereotopic. So I would say that HD and HE are different and they are diastereotopic. Why are they diastereotopic instead of just plain different? For this, the thought experiment might help illustrate this. Again, in the thought experiment, you replace one of the 2 groups, let's say HD, with something else like the Q, and then you replace HE with Q, and then you ask yourself, what is the relationship between those 2 molecules? They are stereoisomers of each other, and in fact, they are diastereomers. If in the thought experiment they are diastereomers, then the protons in the original compound are diastereotopic. Okay? Questions about that? Yeah.
Can you show an example, but like in an example where there would be diastereotopic?
In what scenario would they just be plain different? This CH2 group and this CH2 group are just plain different. They're not attached to the same carbon. Different environments. Okay. Let's look at cycloalkanes. This is cyclopropane. How many kinds of protons do we have in cyclopropane? A, B, C, D, E, and F. 6 protons, but how many different kinds of protons? Some of you were saying 4. Some of you were saying less than 4. Some of you were saying 1. Okay. The ones are right. There is only one proton, one kind of proton, and one NMR signal in cyclopropane. Let's see why that's true. And let's see what kind of same they are. So first, there is a C3 axis of symmetry that goes right through the ring. A C3 axis is 120 degree rotation. Can you see that 120 degree rotation brings HE to where HA is? And vice versa? You do that 3 times and you've interchanged everything. Okay. Now let's do above the ring or below the ring. Those are clearly related by a mirror plane, but they are also related by a C2 pancake flip axis that will interchange HA and HB. So all of the protons are homotopic, and there's just one kind. Now, if we change that briefly, any questions about that? One kind of proton? Yes?
So, I thought since like planes of symmetry were used, that would be an antiatomic.
Right. The question is, you're seeing that HA and HB are interchangeable both by a C2 axis and by a plane of symmetry. The axis has precedence. So if you can find the axis, they're homotopic. Yep. Good. All right, let's change the cyclopropane just a little bit. Let's turn one of those protons to something else. That's going to break some of our symmetry. Now, because of the chloro group, we no longer have C3 symmetry. You can't do steering wheel action by 120 degrees and get the same thing. We also lose this pancake flip axis of symmetry, because if you flip it over, now the chloro's a wedge instead of a dash. So that's not there anymore. We also lose the mirror plane of symmetry that's the plane of the page, because what's above the ring is different from what's below the ring. So that changes everything. How many protons do I have? How many different kinds of protons do I have in chlorocyclopropane? Some of you are saying, I'm seeing 5, I'm seeing 7. No, nobody's doing 7. Okay. Clearly HA is its own thing. What about HB and HC? Are they the same or are they different? They are different because HB is cis to the chloro and HC is trans to the chloro. What kind of different are they? Just plain different or diastereotopic? Very good, diastereotopic. And in general, in cycloalkanes, if it's a cis-trans issue, they're diastereotopic. Good. So HB and HC are different, and they are diastereotopic. What about HB and HD? They the same or different? Okay, they are the same. What symmetry operation makes them the same? There's a mirror right there. What's on the left is a reflection of what's on the right. The mirror coincides with this chloro, this hydrogen, and that carbon, and it splits these two carbons in half. So by mirror symmetry, HB and HD are equivalent to each other. That makes them what kind of topic? Enantiotopic for the mirror, not the axis. Enantiotopic. And then HC and HE are also enantiotopic. So we expect three signals. B and D are enantiotopic, C and E are enantiotopic. Yes?
Are the three hydrogens that are on dashes, could you not rotate them around the plane to the middle of the triangle so they would be homotopic?
No, the three protons that are dashes, HA, HC, and HE, you could do steering wheel action to rotate 120 degrees, but remember, to be a true axis of symmetry, the rest of the molecule must appear unchanged. Because of the chloro, when you rotate, suddenly chloro is no longer here, it's down here. Yeah. I saw another hand, yeah.
When we say enantiotopic versus stereotopic, is that just in relation to whichever hydrogen we're comparing to?
That's right. Enantiotopic and diastereotopic are a relationship between protons. So you're never going to look at a single proton and say, is it homotopic or enantiotopic? It's always going to be a relationship among two or more. So that's why I'm saying B and C are diastereotopic, but B and D are enantiotopic. Yes?
So I have two questions. Would B and E then be homotopic?
B and D?
B and E.
B and E, what would you call the relationship between B and E? They're not on the same carbon. I'm not sure. Yeah, that's a good question. B is diastereotopic with C. C is enantiotopic with E. So does that make B and E also diastereotopic? I'm not sure. So I'm going to punt on that one.
And then my second question was, if this wasn't in a ring, but if it was opened up,
Yep.
would it change anything?
Right. So if this wasn't a ring, if it would open up, would that change everything? And the answer is So you want to do this example. And you want to ask, what's the relationship between HA and HB? This is tricky. What you have to do is look and see, is there any axis of symmetry or mirror plane of symmetry that makes HA and HB identical to each other? I don't see an axis of symmetry that makes A and B identical to each other. I also don't see a mirror plane of symmetry that makes HA and HB identical to each other. You could say, well, isn't the mirror the plane of the page? And I'd say, yeah, fine, but the chloro is not a reflection of the hydrogen. So if there's no axis and no mirror, but they're on the same carbon, you have to conclude diastereotopic. Now, one other way you can verify diastereotopic is, again, through the thought experiment. So in this case, replace HA with the some group Q, and then replace HB with some group Q, and ask what's the relationship between the two. Those are clearly diastereomers, and therefore it has to be diastereotopic. So your answer is no. You can have diastereotopic protons even in molecules that are not rings. Yes?
What would a test question look like on this?
A test question would look exactly like what we've been doing here. What is the relationship between those two protons? You choose A, an homotopic, B, an antiotopic, C, diastereotopic, D, just plain different. Yeah?
Can you ever have just plain different hydrogens attached to the same carbon?
Can you ever have just plain different hydrogens attached to the same carbon? I can't think of any examples like that. If they're attached to the same carbon, it's going to either be the same or diastereotopic. Yes?
I'm confused why there's not a mirror on this molecule, but there is on the very last example.
Why there isn't a mirror here?
Yes,
What mirror are you looking for?
between D and E.
So you're saying if I reflect, you're saying the mirror plane is perpendicular to the plane of the page and it reflects D into E?
Right.
The problem is that's not a valid mirror because the chloro is not a reflection of the methyl.
So on the next example, just below it, how come that's a mirror, but then the chlorine?
The mirror plane here contains the chloro and the hydrogen. It's like we're fruit ninjaing the molecule in half. I was never very good at that. All right. So now we need to talk about two more things today. Position of NMR signals, that is, what is their chemical shift and what information you can get from that. And then second, the shape of the peak or the splitting of an NMR signal. So first, the position of signals, chemical shift. To understand this, you got to know something about electrons. And that is from physics that in the presence of a magnetic field, electrons tend to circulate, and circulating electrons generate their own magnetic field. So zooming in on this diagram, here is an isolated nucleus that is not surrounded by electrons. It experiences only the external magnetic field, the orange B0. Here is a proton rather, surrounded by electron density. We're not saying how many electrons, we're just maybe these are electrons in a bond that the proton is involved in. They tend to circulate in a way that opposes the external magnetic field. Now, because this is a chemistry textbook and not a physics textbook, I'm not sure whether the black arrow represents the actual movement of electrons or the movement of current, which is opposite in physics. Thank you, physics. And then I actually don't remember the right-hand rule very well for which direction electrons circulate versus where the magnetic field goes. Sorry, I got nothing. So, but in any case, the electrons circulate in a way that generates a smaller mini magnetic field. We call it an induced magnetic field, which I am giving the name B, lowercase b with a subscript I. And it turns out that that induced magnetic field most often opposes the external magnetic field. So it's like the circulation of electrons around a molecule is insulating or protecting that hydrogen, that proton, from the external magnetic field. We call it shielding. And if you like to play Star Wars, Starfighter video games, shields are a very important aspect of surviving. It has nothing to do with this phenomenon. But we're going to talk about shielding the nucleus, which means it's in an electron-rich environment. Now, fortunately, you have a lot of good intuition already in this class for electron-rich versus electron-poor environments. And one of the most useful tools is electronegativity. So let's just say a proton that is in an electron-rich environment will experience the external magnetic field minus whatever the strength of that induced magnetic field is. Now, if you remember, the strength of the field determines the separation between spin states being aligned with the field or against the field. And that separation in spin states determines the frequency that a proton absorbs at. So, bigger field, bigger splitting difference, bigger frequency of absorption. So we will see that a proton that does not have any shielding because of electrons absorbs at a higher chemical shift, higher field experienced, higher separation between spin states, higher frequency, than a proton that is surrounded by electrons. We will say that a proton that appears at lower chemical shift is de-shielded. And chemists will also use the word upfield to describe the shielding direction or lower chemical shift. Yes?
Can you explain that one more time? The, the directions, because why is it being de-shielded if it's shielded with the electron?
Yeah, I did that wrong, sorry.
Oh, okay.
Lunes. All right, so Spanish speakers, did you learn to say miércoles instead of another word when you were angry about something? Is that a thing? Okay. No? Okay. So anyway, a proton in an electron-rich environment will be shielded. There we go. Shielded from the external magnetic field by the electrons. And we say being shielded is being moved in an upfield direction. I don't know where the upfield term comes from. Somebody explained it to me once and it made no sense. So, okay.
Can I ask you a question?
Yeah.
So when you go up the graph, you're actually decreasing frequency, which is adding electrons and shielding it?
No, when you go to the right, you are decreasing frequency. That means lower energy gap. That means lower field experience. That means more shielding. To the left is increasing chemical shift. That means increasing energy gap. That means increased experienced field. That means de-shielding. So as an example, you would expect that if this is the chemical shift for this, if this is the signal for methane, if you do chloromethane, chlorine being more electronegative than methane, should pull electron density away from the carbon and therefore away from the protons. The protons here should experience a de-shielded environment, should have a larger energy gap, larger frequency. We say that the protons in chloromethane are de-shielded relative to the protons in methane. Okay? So we can use this to draw some conclusions about where we expect protons to show up. And sometimes relative expectations are good enough. For example, being adjacent to chlorine means you are more de-shielded than being not adjacent to chlorine. And these shielding and de-shielding effects track with distance from the electronegative group. So a proton that is 2 bonds away from chlorine, yay, thank you for that. That's great. Somebody's drilling something out there. I don't know. The protons that are adjacent or 2 bonds away from chloro are more de-shielded relative to the protons that are 1 to 3 bonds away from chloro. Similarly, being close to a more electronegative element means you're more de-shielded. So HA is more de-shielded than HB because HA is closer to fluorine, which is more electronegative than bromine. You follow? Okay. Similarly, it's somewhat additive. So if you're adjacent to 2 chlorines, that's more de-shielded than being adjacent to only 1 chlorine. So you can follow these expectations for shielding and de-shielding. Now, I want to talk about ranges of chemical shift real briefly. You will have a table on your exam that will contain this information. In fact, behold the table on your actual final exam. Somebody has asked me to post this on Learning Suite so that they can help practice. And if I posted all of the pages, they said, they didn't actually say that, that would be tremendously helpful. But that is the NMR table that you will see on the final exam. That's the IR table. Some of you are saying scroll up. Whoa. Torture, yes. Yes. Okay, hold on. The question was, are there any other what?
NMRs, regions, or distances that we need to know that won't be included on that little guide?
Is there anything not included on that guide?
That we'll need to memorize like we have had in other past.
There's nothing I'm going to ask you to memorize that's not on that table. Yes?
You talked about how there's different NMR amounts because of the electronegativity and the shielding.
Yes.
How would that change if it's a diastereotopic?
Right. So one question that's asked, and this is a great question, if two protons are just plain different, how different is their chemical shift going to be? Because I think you're asking, they're both 1, 2, 3 bonds away from chloro. So they might have similar environments. In general, diastereotopic protons are going to have very similar chemical shifts. So not going to be too far apart on the NMR spectrum. Yeah.
So for the NMR spectrum, an antiotopic and homotopic are the same, like, same peak?
Yes.
And
Homotopic and an antiotopic are going to be the same peak because they're identical. Diastereotopic is going to be two different signals. All right. Yes?
Were you recording this?
Am I recording this? Looks like it. Yep. Okay. So I want to tell you about chemical shift real briefly. Most of this is going to track what you would expect with electronegativity. There are some exceptions. You won't have to know why they happen, but it's somewhat useful to have a sense for that. So first, alkyl protons, protons on carbons that aren't attached to electronegative atoms, where these R groups are alkyl. Those show up in the 1 to 1.5 area of the spectrum. And primary alkyl groups are more shielded relative to tertiary alkyl groups. That's just because carbon is slightly more electronegative than hydrogen. Generally, the meaning between these, the distinction between these is not going to be that useful to you. You won't necessarily use it to get a lot of information, but protons in the shielded region from 1 to 1.5 tend to be on isolated alkyl protons that are not adjacent to electronegative heteroatoms. Now, if you replace one of those alkyl groups with an sp2 carbon, whether that's an allylic carbon because an allylic hydrogen because you're adjacent to a carbon-carbon double bond, or a carbonyl group where Z is an oxygen, or even a weird functional group that you haven't encountered yet where Z is a nitrogen, the proton that's adjacent to a pi bond will show up around 2 ppm chemical shift. A proton on an alkyne will show up at around 2.5. That doesn't seem weird to you now. It will in just a second, and I will explain why it shows up here. Protons that are 2 bonds away or adjacent to electronegative heteroatoms show up around 4 ppm, 3 to 4 ppm. Protons that are on sp2 carbons show up from 4.5 to 6. Those are vinyl protons. It makes sense that they should have a higher chemical shift than an sp3 CH bond because sp2 carbons are more electronegative than sp3 carbons. But sp carbons are more electronegative still. So why does an sp carbon show up shielded relative to, why does an sp-CH bond show up shielded relative to an sp2-CH bond? And the answer has to do with a particular way that protons, that electrons circulate in pi bonds. Electrons in pi bonds are held more loosely, and they are freer to circulate in the presence of a magnetic field than are electrons that are in sigma bonds. In an alkyne, the electrons circulate in a pattern that generates a magnetic field where the field lines look like this in orange. They tend to align with the external magnetic field around the side of the alkyne, but where the alkyne proton is, they tend to align against the magnetic field. So the alkyne proton is shielded relative to where you would expect it to be. This happens to some extent with the alkene, but for a bigger extent with a benzene ring. Because benzene is a ring, the electrons in benzene can literally move in a circular pathway. And that induces a magnetic field that opposes the external magnetic field in the center of the ring, but reinforces the external magnetic field out where the protons are. So the protons here experience more of a magnetic field than they should because of the ring current, and therefore they show up in this much more deshielded region of the spectrum, 7 to 8 ppm. Aldehyde protons show up around 9 to 10. Carboxylic acid protons show around 10 to 11, 10 to 12. And then what about protons that are attached directly to electronegative heteroatoms? It turns out, for reasons we don't have time to talk about, the chemical shift of these protons are highly variable. And sometimes these protons don't show up at all, in particular if the solvent you're using hydrogen bonds with the OH group or the NH group. Sometimes the protons aren't even visible in the spectrum. So we may or may not get any information about OH or NH bonds in an NMR spectrum. You kind of have to play loosey-goosey with those and just deal with them after the fact if you have to. That's where an IR spectrum will be particularly useful because the presence of an OH in an IR spectrum is pretty obvious. Yes?
Do we have to have all these numbers memorized?
No, you don't have to have them memorized. They are in the magic table that I showed you. Yep. All right, so let's talk briefly about relative peak area. I mentioned this already. So from chemical shift, you get what are the nearby functional groups, what is the electronic environment, are we shielded or deshielded? From the area under the peak, we get relative numbers of protons. I already showed you this spectrum from tert-butyl methyl ether, where there are 9 tert-butyl protons and 3 methyl protons. And I showed you how the relative areas underneath each of these peaks is proportional to the number of protons the peak represents. So this peak is 1 and this peak is 3. So when I look at relative peak area, I'm not going to necessarily know absolute numbers of protons. I'm not going to know whether this peak means 3 to 1 or 6 to 2 or 9 to 3, but whatever the ratio between those peaks is, it must be consistent with the ratio between the actual number of protons. Yes?
So I know that, relative area under a curve is a little bit more complicated than just like the height of this spike. So
That's right.
it doesn't look like it is a 1 to 3. Do we have to be told the relative area?
Yeah, somebody will, this line here represents the computer measuring the relative peak area.
Okay.
So if that line is displayed for you, you can actually measure that line and measure this line, and the length of those lines will tell you what the peak area is.
Okay, so rather than the height of the
Peak, it's the height of this integrated curve. Or sometimes they will print out the peak area for you. Now, if they print out the peak area for you, if this one were, say, 17 arbitrary peak units, the units don't mean anything. They're not like cubic or square centimeters or whatever. There's some arbitrary peak unit, but they're all normalized. This peak area might be, let's see, what's 3 times 17? It's 51, right? It might not be exactly 51. It might be like 54. And you have to be okay with it not being exactly on. I know some of you would like it to be exactly on, and some of you are going to say, well, what if it's 3.07? What then? And I'm going to say, you ever heard of such a thing as 0.07 of a proton? The answer is no, round down. What if it's like 3.4 or 3.5? Well, make a judgment call, but use your best judgment and understand that protons, identical protons, usually come in groups of 2 or 3. It's kind of hard to come up with an identical group of 4 protons, all right? Unless you're in methane. Okay, so what we need to talk about now is perhaps the most complicated thing of the NMR spectrum, but it's the most informative one. And this is peak shape or spin-spin splitting. So behold the NMR spectrum of 1,1,2-tribromoethane, where you have 2 bromos on one carbon and 1 bromo on the other carbon. You expect there to be 2 NMR signals. The red protons, which I'm going to call HA, just call both of them HA, and then the blue, where did I get green from? The blue proton, which I'm going to call HB. And if you look at the signal for HA, it's one signal, but it's divided into 2 lines or 2 peaks. And this peak is called a doublet, and importantly, the area underneath those 2 peaks is a 1-to-1 ratio. Okay? The peak for B, HB, is split into 3 lines. It's called a triplet, and the area under those 3 lines has a 1-to-2-to-1 ratio. That's important because those ratios help you distinguish a group of peaks that comes from one signal from 3 peaks that are unrelated to each other and are just 3 different signals. Yes?
Is it always going to be that pattern where the lowest one's first? And then
A triplet will always be in a 1-to-2-to-1 ratio.
sorry, I'm like saying the heights though. Like the first one is going to be the smallest.
No, in fact, I am entirely disregarding the fact that this peak is slightly smaller than this one. The patterns are sometimes not perfect. They're sometimes a little wonky.
It's just the fact that the triplet.
Yeah. The triplet, though, refers to 3 peaks in a roughly 1-to-2-to-1 pattern. So you're saying, you're telling me this isn't exactly 1, and I'm telling you we're rounding up. Yep, go ahead.
So will we have to look very closely to see if it's a triplet, or will it say triplet?
You'll have to look and see that it's a triplet. And if you need to look, it'll either be clear. If you didn't have the zoom in, you could still see the 3 lines here in a 1-to-2-to-1 pattern, and that could tell you that it was a triplet. Often, though, it will be zoomed in for you so that you can see it. Okay? So now, yeah, go ahead.
So what exactly does a doublet or a triplet tell us?
Right. So the doublet tells you that the HA protons are next to 1 and only 1 other proton. The triplet pattern tells you, the triplet pattern tells you that the HB protons the HB proton is next to 2 and only 2 protons. So you get nearby connectivity. Now, why is it that way? That's going to take a little bit of explaining, and it's going to take longer than 30 seconds, but we'll do our best. We're going to imagine for the moment that we are proton A. We're standing on that carbon, and we're looking around us to see what the environment is. On proton A, we experience the external magnetic field B0, but we remember that proton B is also a little magnet. And in that external magnetic field, proton B can either be aligned with or against the external magnetic field. And the probability of those 2 events, like I told you last time, is about 50-50. So it turns out the A protons experience 2 distinct environments. 50% of the time, HB is aligned with the field, and 50% of the time, HB is aligned against the field. And that's where we get the doublet pattern. I will explain that in more detail next time, and then we'll finish up on NMR.